Welcome back. So we were talking about advanced learning algorithms. In particular, we talked about the notion of adaptivity. In this lecture, we're going to talk about another key ingredient of advanced training algorithms that we see to be quite essential in terms of both generalization and optimization performance of deep learning models. And that component is called momentum. So we're going to talk about momentum by taking two perspectives. The first perspective is a classical physical perspective, and another one is through the lens of bias variance reduction. So let's start with the first perspective. Okay, so as I said, we're going to take a physical perspective. In particular, we're going to associate basically the evolution of the parameters with the movement of a ball going downhill. Okay, so what do we want to do in optimization? We want to basically find the location that minimizes the loss function. Okay, so in this example, we're going to basically associate the loss with the potential function, such that when the ball is moving downhill, it's going to hopefully reside in at a place with low potential energy. Okay, so we have this ball going downhill. And as I've written here, the ball will eventually stop somewhere with locally low potential energy. So it starts here, okay, and then it gradually is going to drop, given that point A is at higher potential than, let's say, this point, okay. And once it gets here, it may stop, okay. So it may stop. It's not necessarily going to go uphill again, okay. But it may go uphill, okay, so depending on the landscape, depending on other forces that might impact the movement of the ball, the ball could go uphill, okay. In particular, it can gain some momentum when it's going downhill, such that the momentum is going to help the ball to go uphill. And if the momentum is large enough, it may pass this point. The ball may pass this point and actually come in this region, such that it may actually stop at a globally low potential energy as opposed to a locally low potential energy. Okay, so we're going to basically see what will happen here. So what are the forces impacting the movement of the ball, and what are some conditions such that we have this build-up momentum that I talked about that could potentially help us to escape local solutions and find global solutions. Okay. Now, as I mentioned, we are basically talking about the movement, right? So, and the movement of the ball is actually perfectly described by Newton's second law of motion. So that basically says that force is equal to mass times acceleration. Okay. So in this example, we're going to assume that the ball experiences two forces. Okay. One force is due to the potential energy. So I'm going to assume that the potential energy is basically F of W. The higher the ball is, the higher the potential. The lower the ball is, the lower the potential. Okay. So the force associated with that from physics is, and it's not very important for us, is going to be basically minus the gradient of the potential function. Okay. And there is another force called the drag force, which is, in this case, I'm assuming a linear drag, which is sort of proportional to the velocity of the ball. Okay. Now, putting these two together, we're gonna arrive at this equation. Again, mass times acceleration is just some of the forces that the ball experiences. Okay. So in this case, I have two forces: one due to the drag, okay, another one due to the potential. So this is a second-order ordinary differential equation. It can be written in terms of a system of two first-order ordinary differential equations. So as I've written here. So these two are equivalent. And the reason I'm writing in this form is that now we can basically talk about the momentum. Okay. So momentum from physics, you may know that momentum is basically mass times velocity. So m times w dot. Okay, so this is basically written in terms of the momentum. And as I mentioned conceptually, if the ball has a sufficiently large build-up momentum, and also depending on the strength of the drag force, okay, the ball basically could reside at the point with the globally lowest potential, meaning that it may escape this local solution and find this global solution, okay? So let's consider, therefore, a couple of cases, okay? A case where we basically don't have any momentum and another case with momentum. And let's see whether what's the analogous optimization algorithms for these two cases. All right. So let's first talk about the simple case where there is no momentum, okay? And what I'm going to consider basically, when we say there is no momentum and momentum is mass times velocity, that basically means that the mass is 0. So we're going to assume a massless particle, okay? Or a light ball, if you will, okay? And again, just some technicality here. We have to assume that the velocity is less than the speed of light, such that the momentum is 0. So that's basically the merit of the story. The momentum is 0. Therefore, our physical law reduces after some rearranging to this equation, which says that velocity is just minus some constant times the gradient of the potential function. Now, this is basically called the gradient flow. Okay, so this equation is called the gradient flow, and there are lots of studies about convergence of this ordinary differential equation. One way to solve differential equations that we have talked about in the class before is basically utilizing numerical approximation methods such as Euler's discretization. So we can discretize this equation in time domain, in continuous time to a discrete time. And upon doing that, we're going to arrive at this equation. Okay? So hopefully this is a familiar equation to you. This is nothing but the update of gradient descent, which says that we're going to basically go from one solution to the next by going in the direction of the negative gradient while using some learning rate. So this is exactly gradient descent with learning rate 1 over rho. Okay? So therefore, the case where there is no momentum, so therefore there is no build-up momentum, and we're not going to be able to basically avoid the local solution, is going to lead to an algorithm we've talked about extensively in the class before, and that's gradient descent. Okay? So therefore, gradient descent is sort of associated with the trajectory of a massless or light ball. Momentum is 0, and therefore, at least intuitively, we can expect not to be able to avoid getting stuck in a locally low potential state. Meaning that if this was, again, our landscape, my gradient descent algorithm is going to start here, and then it's going to converge to this point. And I may not be able to sort of find this better solution. Hopefully, momentum is going to help us to actually avoid this case. Okay? So therefore, let's talk about the case where the ball is heavy. It's not light, it's not massless, it's heavy. Okay? And again, let's use the Euler's discretization. And after some basic manipulation and also renaming the constants as appropriate, it's not too difficult to show that the discretization of our second-order differential equation is going to lead to this equation, to this update. Okay? Equivalently, again, we can represent it as a system of two first-order differential equations, discretized those, and then we're going to arrive at this as this update. Okay? Now, this is exactly the method we refer to it as heavy ball gradient method in optimization. Okay? Where beta in this, there are two parameters. First of all, there is the learning rate that we've talked about before, exactly the parameter we use in gradient descent and stochastic gradient descent. But there is also a new term, beta, that sort of controls the momentum, and it's called the momentum parameter. Okay? So in particular, here is the momentum term. Okay? So let's first look at the first way of writing the heavy ball method. If beta is equal to 0, we are basically going back to the gradient descent algorithm. On the other hand, if beta is large, then this term is going to be large, and hopefully it's going to help us to find better solutions, okay? So the momentum in this case is just the difference of two consecutive updates. Equivalently, we can refer to this equation, okay? So it says that we're going to use the same update as we had before. Again, we're going to go using a first order update from the current solution to the next one by taking a step along some vector, in this case not the gradient, but the momentum vector p, okay, with some learning rate. And here is how the momentum is updated, okay? So you basically consider what the momentum was, you multiply by some constant beta, and then you add up to it to the current gradient. Again, we can see here if the beta, the momentum parameter, is 0, the update vector we are using in each iteration is exactly gradient, and the method reduces to gradient descent, okay? But the idea is that, again, this correction term we are adding hopefully is going to aid us reach higher quality solution compared to just simple gradient descent, okay? Meaning that we may escape hopefully locally low potential energy states and find globally low potential energy states thanks to build up momentum. All right. So this perspective is actually quite useful and has been leveraged in the literature extensively to drive even better algorithms, okay? Here I'm mentioning another method, which is perhaps one of the most important breakthrough in optimization, and that's Nestrov's accelerated gradient method, okay? So the idea, again, by taking this physical perspective, we can manipulate the forces to arrive at different laws of motions. For instance, we can assume that the drag force is actually something that is time varying, okay? So previously it was a linear drag, some constant times velocity. Here there is another constant times velocity divided by t, okay? So and t is the time. And this leads to this second order ordinary differential equation, okay? Again, we can see this t here. And it turns out that this ODE is intimately related to this famous method that I talked about, Nestrov accelerated gradient method, which is written in this form, okay? So again, you're using some update vector to go from WT to WT plus 1 according to a learning rate. But your update vector depends on, which is again the momentum, you can call it momentum, is basically a momentum parameter times the previous version of the momentum plus the gradient. But the difference between Nestrov method and heavy ball method is that the gradient is not calculated at WT, the current solution. It's actually calculated, let's say, at this solution with some look ahead, okay? So you can think of it as basically a prediction of where the next update is going to be. So we're going to basically calculate the gradient at the prediction of the next update and use that to sort of find our momentum vector and therefore update our parameter, okay? So this method is called accelerated gradient method because it achieves an acceleration and an optimal convergence rate compared to gradient descent for a smooth and strongly convex functions. It doesn't have to be strongly convex, so as long as the function is smooth and convex, whether strongly convex or not, this method actually provably improves upon gradient descent. That's why it's one of the most important breakthroughs in optimization literature, okay? So this is one way to think about this method. Again, so you can come up with various optimization algorithms by considering different differential equations. Another way to sort of arrive at a similar algorithm, basically accelerated variance of gradient descent, is to basically come up with better ways to discretize a specific ordinary differential equation, okay? So for instance, instead of the method we use, which is called one-point Euler method, you can use multiple point Euler method, for instance, two-point Euler method, okay? And this will lead you to, again, an algorithm that looks very similar, if not identical, to Nesterov accelerated gradient descent. Okay? So the merit of the story, therefore, is that this physical perspective helps us to gain an intuition of why leveraging momentum, right? So slightly more complicated, if you will, update vectors in our optimization algorithms. And the reason for that is that they may help us to find better solutions faster. Okay? This perspective, again, could lead to different optimization algorithms, again, by designing different differential equations and discretizing them, or using better discretization techniques to solve the original differential equations we talked about. That's basically, I would say, the classical view. So in the next lecture, I'm going to talk about the second perspective, which is more pertinent when it comes to optimization for deep learning. I'll see you next time.